So yeah, all of this was going from bottom to top, which is the reverse of what you should think of as being more basic, which is differentiating, going down. So they're saying, let's have full size. They're saying, please differentiate log x squared. So they're saying, please, can you go from log x squared to the derivative of?
Yeah.
Have you come across this way of writing the derivative of?
D by dx. I think I have, yeah.
Because after all, you're familiar with dy dx, aren't you?
Yeah.
Well, you could think of that as d over dx of. So d dx is just a symbol saying derivative of, and it doesn't have a closing bracket. Integral of has a closing bracket, doesn't it? Integral of, and then close the bracket. But derivative of is just an opening bracket, and then the y, say. But then you can see how dy dx just means the derivative of y with respect to x.
Yeah. Okay. Yeah. See that.
So if the original function is log of x squared, how shall we move from log x squared down to its derivative? So if we were to rewrite it, what would be a good way of writing it to show how we're going down?
What do you mean? To show
well, look at log x squared.
Okay.
How would you pass it?
You could, yeah, you'd probably do x squared as the blob.
Yes, indeed. What you've got here is log of the whole of x squared, which is an inner function, causing what to happen on the way down?
You're going to stay with log, wouldn't you? Oh no, you get 1 over.
Good.
1 over x squared.
Good. Done?
Yeah. Oh no, and then times by 2x.
The derivative of the inner function, absolutely. You've got to do that. Let's simplify.
2x over x squared.
Yes. Simplifying to?
Simplifying to... I don't know how you'd simplify that. Root 2x over x.
Oh. So this says 1 over... So we're multiplying a fraction by something.
Yeah.
For example, if you've got 1 over 324 times, I don't know, 43.
Yeah.
How could you write that?
43 over 324.
Yes. So
that's what I said there.
Oh, so you said what? Sorry.
I said 2x over x squared.
Oh, yeah. Sorry. Yeah.
Why?
Yeah, I think I heard you say that. So why did I get anxious? But again, oh no, that's right. I did hear you say that, and then I said yes, but simplify.
Yeah.
And then, if you needed help with that, but I was forgetting that you had got this far. What you need help with is just simplifying that, isn't it?
Yeah.
Are you sure?
Well,
isn't that just 2x over xx?
Yeah. Oh, yeah. So 2 over x.
So 2 over x, yeah. Which is interesting. I mean, if we were to integrate 2 over x, what would we expect to get? Let's integrate 2 over x.
Wouldn't you get ln x, ln 2x, or 2 ln x?
It would be 2 ln x, wouldn't it? It would.
Yeah.
So what is happening?
So What do you mean? What's that? Well, you're adding a.
Can we reconcile these two?
What
If these two are equal,
Yeah.
and that
Uh,
seems to be the integral of this, but that seems to be the integral of this.
I guess they just equal the same thing.
Do they then? Is log x squared equal to 2 log x?
Probably not.
Probably not, did you say?
Yeah, probably not. Probably not because we haven't added like a you something would get spat out at the bottom.
If you were expanding log of xy, how would that go?
The integral of 2 over x isn't 2 ln x.
Sorry, the integral of 2 over x. Oh, you're disputing this now?
Yeah.
Oh, I am surprised. I mean, you did give me 2 options for that, and I chose the second. I think at
Yeah, no,
first you said ln
that
2x.
isn't necessarily wrong, but wouldn't it also spit out you get an x down the
No,
bottom?
well, no,
Like,
because the inner function isn't just x, and the derivative of x is what's the
the
derivative?
derivative of x is
Respect to x.
is oh my days, 1 times 1 is
I mean, the derivative of 3x would be what?
3.
So the derivative of 1x would be
1.
1.
Yeah, that's what I was saying. You get an x spat out on the bottom, or even a 1.
Just 1.
Yeah.
So we don't have to doubt this, do we? The integral of 2 over x would be 2 log x.
Oh yeah, that's true.
Because this often there's no harm in trying to apply a chain rule unnecessarily, because it's like very often you apply the chain rule in a trivial way where the inner derivative is 1, but it's still useful to apply it. Perhaps not here though. There's no point in applying the chain rule because it's just x there. So we can just think of it as, okay, we can ignore the 2 because you always can if you're differentiating or integrating, can't you? A constant multiple, you can just add that on afterwards. But the derivative of log x is 1 over x, so it's double that.
Right, okay. I see.
Right, but are these two equal? I mean, if these two are equal and the integrations are both okay, surely these must be equal.
Maybe they are. But
maybe they are. What about log of xy?
What am I doing to it?
Can you expand it?
Log x, log y.
Oh, definitely not. We need to practice our logs.
Look, I don't know.
If I say no to that, what would you give me second?
Ln x plus y.
Ln x plus ln y is how it expands.
Oh, okay, right.
It has to do with the fact that, and here's where I stumbled yesterday, wondering whether to explain this properly, because it is mind-bending. But the power you have to raise e to get xy is, so if you think of that as e times something, so x and y are e to something else times e to something else.
Right.
I mean, basically, if that's not x, if that's a and that's b, then that's going to be a plus b.
Right. Okay.
A is the power you have to raise e to get x,
Mm.
which is what that is. B is the power you have to raise e to get y, which is what that is.
Right.
You
Okay.
can see how e to the a times e to the b would be e to the a plus b.
Yeah.
So from that relationship, it's mind-bending, but from that, I mean, by all means, meditate on that whenever you get the chance.
Yeah.
But this is the mechanical rule. Log of x, y equals log x plus log y.
Right. Okay. Okay.
Well, in that case, what about log of x times x?
Ln x plus ln x.
And can you simplify that?
2 ln x.
Which is how log of x squared equals 2 log x.
Oh yeah. Okay. So it does always equal
So here's your another mechanical log rule that you must learn mechanically.
that. Mm.
Log of anything to a power, you can send the power around to the front like that.
Right. Okay.
Log of a to the b in general becomes what?
B log a.
B log a. And then for roots and dividing, you know, it's what you would expect, those versions of that.
Did you mean to change it from a ln to a log?
No, but I was saying log, wasn't I? As I do prefer to. I prefer to call lin log. So
Right.
go changing to that preference led to a typo. Thank you. Yes, good. So the point is here, this power here is coming round the front.
Okay.
That's all.
Right.
Log
Okay.
of a to the b equals b log a in general, because log of xx equals log x plus log x, which is 2 log x.
I see. Okay.
So we've differentiated that, and it's just 2 over x.
Yeah.
Okay. And then you get 3 marks for that. So it's not a nothing question. It's 3 marks. There's more to it than the kind of differentiation you're used to. And now let's do x squared sine 3x. So how are we going to pass this?
Okay.
As a composite?
I think, yeah, so you have sine 3x.
Yeah.
As a blob.
Oh, sine 3x as a blob. I mean, yes, I am going to write it like that. I'm going to put a blob there.
Yeah.
But on the other hand, you know, we're at the top here, aren't we? We're going down.
Mm.
It's not like we've got an inner derivative up here, so we can't say x squared perhaps is the inner derivative, and it wouldn't be anyway, would it? It wouldn't be the inner derivative of 3x.
Mm.
So we need to recognize that what we've got here is a product. That's how we pass it.
Okay. Okay, I see. Yep. Yeah, okay. So then you're gonna get
yeah. What are we going to get down here?
You'll get x squared.
Okay.
And then you'll get cos 3x.
Okay, but there is an inner derivative there, so we must write what?
Cos 3x times 3.
Yeah. So what we'll do is, you see, we won't sort of dwell on that rather simple use of a chain rule.
Mm.
If we're differentiating sine 3x, we just say to ourselves, oh, of course, 3 cos 3x. because of
Yeah.
the chain rule. It's just, you know, as we get used to it, it gets easier.
Yeah.
So yeah,
And then 2x.
oh, don't want to say 3 there, do I? Not at all. Because, yes, I do. Thought I was integrating there. So we're going to have 3x squared. Oh, sorry, I better put the simplified version over here. Or shall I do, what I'll do is I'll say derivative of x squared sine 3x. I think that's what I was trying to do. So what should I put here?
2x
After what crucial symbol?
plus
Yes, that's how the product rule works. It is this product plus this product.
sine 3x.
Okay, are we done?
Um, we could simplify, but
Yeah, apart from simplifying, maybe. Let's try that. But there's not much to take out, is there? There's only
well,
take out. I wouldn't bother. What's to be gained taking x out of there? We'd still have 3x cos 3x
yeah,
plus 2 sine 3x. There's no economy there, is there?
yeah, no, I agree. I think that's probably the best option.
Right. Oh, I didn't think my phone was on vibrate. Right, sorry. So where are we? Right, we're doing that. Whoops. Given that 2y equals that stuff there, find dy dx. Check your answer. It should be sine squared x when you've simplified, but let's ignore that. Let's do it the same. So if 2y equals x minus sine x cos x, so I suggest what we ought to do probably is say y equals what?
Yeah, I was just thinking the same.
Good, yeah.
All of that over 2.
Yeah.
Or
Personally, I would rather divide through by, multiply through by a half is probably my preference. I mean, if you put it all over one fraction, no, you wouldn't know how. That's a backward step, really, isn't it? So dy dx is going to be the d dx of all of that.
Yeah.
Okay, so how shall we pass this?
Well, I'm not entirely. Oh, I guess you do the product rule
For this? Yes. And what about
for that,
this?
and then for that you'd you just, I don't know, differentiate it.
Yeah. The thing is, if things are joined with plus or minus signs, there's no complication. It's just like it is with a polynomial. You do this term and then that term.
Yeah.
So we can differentiate this term and then deal with the product, which is going to be what? How should we pass the product?
Half sine x.
In one part. Good.
Cos x.
And cos x in the other. That's right. We only want the half in one of them, don't we? That's quite correct. So let's start along the bottom here.
A half.
Just a half. Good. And then minus.
Minus a half sine x.
If you like to, I mean, personally, I will tend, if I can, to differentiate rather than having the lines crossed there.
Okay.
So
Well,
just to sort of nudge you into that unimportant preference, I think I will ask you to say a half
cos x.
cos x.
Cos x.
Because I hope you will do these diagrams as kind of carefully as though it is algebra in a way that we're doing here. It's not just a vague wishy-washy thing, is it? It's got a structure to it.
Yeah.
So then what?
Then half sine x.
What, like that?
Plus a half sine
That's
x.
got to have a plus there. But notice there's a bit of a problem there. Do you see the problem?
Minus, it's a minus up at the top.
Yeah. So you could put a minus there, but the product rule really is a plus. So perhaps it's safer to just put a square bracket there.
Okay.
And then finally?
And then minus cos x. Oh, no. Times minus cos x.
Times minus?
Minus sine x even.
Means sine x. Good. Right. And then we need to close the square bracket.
Yeah.
And this does need simplifying, doesn't it, with the brackets and the signs and whatnot. So
you could say a quarter minus a quarter cos x.
Oh, I see. But shall we put this one first?
Which one?
We could put it last if we liked. Yeah. I mean, if you prefer to leave the half till last and put it on the end, on the right-hand end.
Okay, yeah.
But I mean, you are clear that what we've got here is a half minus all this.
Yeah, not times, yeah. Okay, well, a half cos squared x.
Oh, you want to do these first? Okay, fine. It's minus a half cos squared x, isn't it?
Yeah.
And if we can, we like to start with a plus. So we don't have to say plus, don't we?
Yeah.
It's just part of the kind of, not bookkeeping, but it's just part of the tidiness.
So half sine squared x.
So it's going to be plus half sine squared x, isn't it? Because it's going to be minus half sine squared x, but we're subtracting it. So we might as well start with half sine squared x
minus half cos squared
x minus a half cos squared x. Then what?
Then minus a half, plus a half even.
Plus a half even, yeah. Good. Ah. So that looks nice and neat. And yet, it's not what they've got.
Yeah, well, you could, I don't know, you could factorize that.
Not much. We could take a half out. Well, let's do that.
Yeah, because then you'll
that would help.
Yeah.
That might give us some ideas.
Sine squared x minus cos squared x. And then you could change minus cos squared x into 1 minus sine squared x.
Yes. Excellent. dear. Oh yes, oh dear, because we need a bracket here, don't we?
Yeah, so it makes it
Yeah.
plus.
Yeah. Absolutely, yes. Cos squared is 1 minus sine squared plus 1. And now what?
Then you'll have half 2 sine squared x.
And then the ones cancel.
That's it, yeah. And then
It's
times
perfect.
that by sine squared x.
Right. So that's more differentiation. Notice we've got the linearity I mentioned yesterday. The fact that you can differentiate or integrate term by term as long as the connections are plus or minus.
Yeah.
Derivative of this minus the derivative of that. And we've got a product rule. Now, find the coordinates of the points of inflection of the curve.
Okay.
Oh, but by the way, what can I just ask you a related question?
Mm-hmm.
What's the integral of sine squared?
The integral of sine squared, would it be cos squared? No. I know what it. Sine squared. Would it be like a sec squared or something? So
No. Where did we get sine squared from?
1 minus. Would,
All these equal signs go back to this line here.
yeah. Well, we had sine times sine.
Sorry?
So, well, if you go up a bit more,
The point is, this is what we've got on this lower row here. Look at all the equal signs. That
yeah,
bottom
so,
row just is sine squared.
yeah,
So what's the integral of sine squared?
sine x, half sine x cos x. No,
Subtracted from?
subtracted from a half x.
Yes. So it's important to appreciate this just is sine squared x in an unobvious guise.
Yeah.
The integral of it is going to be half x minus sine x cos x, which might be one of the simplest results from trying to integrate sine squared. We would use various ways. Yes, we would use integration by parts, possibly, but there's other ways. We could use a double angle formula as well. But the point is, this would be the fact that we're working backwards through the product rule here is, although we did some Pythagoras first to make it neater, but we could have just applied the product rule straight away and done it by parts, but it wouldn't have been quite like this. But it would have been an interesting by parts exercise, which we ought to do sometime.
Okay.
But I just want to stress that, you know, what's happened here? Sine squared x basically down the bottom. Therefore, the integral of that is going to be all of that.
Yeah.
Find the coordinates of the points of inflection of the curve. Do you know about points of inflection?
Yeah, it's the point where the gradient is 0.
No, those are called turning points.
Oh, the points of
And how do we find the turning points of a curve?
where the gradient equals 0.
So how would we find the turning points of this curve?
Set dy by dx equal to 0.
Yes, we would. Points of inflection are a bit different to turning points. A lot different. Points of inflection are roughly here, here, and here.
Okay.
And what's happening at a point of inflection, do you suppose?
It passes. I don't,
I mean, it might be roughly, very roughly speaking, it might be roughly halfway between the turning points. It might not, though. It depends on the curvature. But the point of inflection is about the curvature. Look at the curvature here. It's like you're turning anti-clockwise, and eventually you would end up doing that, maybe. Whereas after the point of inflection, oh, sorry, I don't know my clockwise from anti-clockwise, do I? Clockwise before there, anti-clockwise.
Yeah, where the gradient like goes from one.
Well, yeah. What's going on with the gradient at the point of inflection? The thing is, the curvature, the gradient here, what can we say about the gradient at this point?
It's positive.
Yes, and the gradient here is?
Negative.
But the curvature is still clockwise.
Yeah.
Whereas the gradient's negative here, but even when it becomes positive, the curvature is still anti-clockwise.
Yeah, okay.
So the first derivative, you know, could be positive here, negative there, but it doesn't tell us anything about the curvature. What we want to know is where the curvature is changing from clockwise to anti-clockwise. Okay?
Right, okay.
And we just accept, really, we won't go into the theory of it, but we'll just accept that the way to find, well, the way to establish whether your curvature is clockwise or anti-clockwise is to see whether you are headed soon down or you are headed soon up. Resist the temptation to go back again, because then you haven't got a function, have you? You've got a one-to-many relation.
Yeah, yeah, of course. Yeah.
But if you are headed soon down, then your second derivative is, can you guess?
Dx squared?
Negative.
Yeah.
If you're headed soon down. And if you're headed soon up, and therefore tending anti-clockwise, then your second derivative is?
Positive.
And therefore, if you are at a point of inflection where the curvature is changing from one to the other, your second derivative is?
Neutral, I don't know.
Yeah?
Zero?
Yes. Okay, so you're using the first, you're setting the first derivative to zero to find the locations of what?
The locations of the turning points.
And then you're using the second derivative set to zero to find the locations of the
inflection points.
Yeah.
Right, okay.
Okay, so that's what a point of inflection is.
What, so you differentiate and then differentiate again?
Yeah.
Okay.
And set the second derivative to zero will give you the points of inflection. So how should we find the second derivative here?
Didn't it get to sine squared x?
Did it?
Yeah.
What was sine squared x the value of the expression for?
Half x minus half sine x plus x.
But it was the what? The result of doing what to the y values, to the y expression?
Differentiating it.
Differentiating it how many times?
Once.
Once. Sine squared x is what we call the first derivative of y.
Yeah. Yeah.
But we just agreed the first derivative is only good for finding the...
Yeah, so differentiate sine squared x.
Yes, with respect to x.
Yeah.
Okay. So we've got another differentiation problem. Sine squared x, we want to differentiate it. What's the derivative of, with respect to x, sine squared x? Opening bracket there again. no closing bracket. It's just the way we write it. Derivative of sine squared x. So how shall we pass sine squared x in order to be able to
We
differentiate?
make x the blob.
X is blob. We found that having x as blob is a fairly...
So we're just going to get 1.
Sorry?
So we're just going to get 1.
Yeah. So how would that pan out? How would it help us? I mean, not much. We'd still have to decide how to differentiate sine squared of that.
Yeah, okay.
So that didn't really help us. How shall we pass sine squared x?
Would it be like the whole thing?
Sorry?
Would you just do the whole thing as blob?
Okay. That's an interesting idea. I mean, we could. What's the derivative of x with respect to x?
1.
1. So what's the derivative of blob with respect to blob?
Blob.
No, because x
Blob.
wasn't x.
Blob.
I mean, if we differentiate x with respect to itself, we get 1. If you differentiate anything with respect to itself, you get
1.
1. So that would be all very well. With respect to blob, we get 1, but then we must differentiate by the derivative of the inner function.
Yeah.
But then we're back to the same problem, aren't we? Sorry, it wouldn't be sine squared x. It would be the derivative of sine squared x, whatever that is. But then we're no better off, are we? We've still got to differentiate sine squared x.
Yeah.
So that's the other extreme. If you take the whole thing as the blob,
yeah,
then it was just 1 of that to the power of 1. So you get 1 times 1 is 1. Reduce the power by 0, by 1 to give 0. So it's 1 of 1. So it just didn't do us any good. So let's have another go at passing this.
Sine squared. I don't know, just sine.
Yes. We haven't tried that yet, have we? And the outer function is?
Squared.
Because that's what's happening in sine squared x, isn't it? It is the square of sine x.
Yeah.
There's your composite. Inner function, outer function. Okay.
Okay, so you
with
get,
respect to blob, what do we get?
2 sine x.
Yeah.
Cos x.
And because of that, 2 sine x cos x. Excellent. Done.
Yeah.
Neat, isn't it?
Yeah.
Nothing more to do. I mean, when you're differentiating, there won't be any adjustments, probably. There might be simplifying, but not adjustments. You just make it work. All of the integrating we've been doing this week is like much harder because
you don't have to go back and
you've got to go backwards. Yeah. Right. So what were we doing? Finding the coordinates of the points of inflection of the curve.
Yeah.
And what have we just found?
We've just found that 2 sine x cos x is going to be set to 0.
Yes, because it's the second derivative. It's d squared y over dx squared, we write it. Don't worry about the squaring. Don't take that literally.
Okay.
It's just saying second derivative.
Yeah.
Just like dy dx says the first derivative. Right. Okay. So we're going to set that to 0.
Yeah, I think so, yeah.
Yeah. Where should we go from there? What does setting this to 0 tell us? What can we deduce next?
We could now say...
I mean, we're trying to solve that equation, really, aren't we?
Yeah.
That equals 0. How would you solve 2 sine x cos x equals 0?
Would you try and bring something to the other side or not?
I mean, it's a tricky one. Or is it? Sorry, it's not necessarily tricky, no. You've got a product equal to 0. I mean, I was going to say, oh, it's tricky because you've got to think of using a double angle formula. Because you could say, do you know what that is as a double angle? It's the expansion of what double angle trig function?
It's the expansion of sine 2x.
It is. Good. So it's sine 2x, which is equal to 0. In which case, sine 2x itself must be what? Now, unit circle. Sine means what? The sine of an angle on the unit circle is what feature of the point on the circle at that angle?
Opposite over the adjacent. Is that what you mean?
It's sine. Sokotoa says sine means what?
Opposite over hypotenuse even.
Right. And if the hypotenuse is 1, we can ignore it because it's over 1. So sine just means
opposite.
Opposite, which is what feature of the point on the circle?
The height.
The height given by the
y value.
The y value for that point on the circle, right?
Yeah.
So what points on this question here becomes, what points on the circle have a y value of 0?
Okay, so 0, 180 degrees.
Yes, good. Now that's a point. They're in radians. So we'll say what?
Pi.
And
0.
Yeah. Now they've got strict inequality there, so they're not including 0 and 2 pi. That's a bit weird because I don't think we're going to get more than one inflection point then. Yes, we are. I beg your pardon. Yes. So because they're not including 0, because look, the domain says well, anyway, no, we'll put them both. 2x equals 0 or pi. And let's put 2 pi if we like. Because we don't have to deal with the restriction yet.
Yeah, so and then x is going to equal pi over 2.
Pi over 2 or
pi.
Or pi. So it was important that we included 2 pi even though...
Wouldn't we do a few more then? Because you're going to be... Wouldn't we do like...
Good point.
3 pi over 2.
Well done.
I went in the
quite
bottom.
Right, quite right.
In the x one.
I nearly missed that. And then 4 pi. And then here we would also need... Oh, I beg your pardon. I'm completely up the creek here, aren't
I meant 3 pi over 2 in the bottom one.
Yeah, exactly. So you did. Pardon me. Complete typo. 3 over 2 pi here. Well done. And 2 pi, but then we wouldn't include that one, would we? Or that one?
No, yeah.
So these are our solutions. Oh, sorry, those are the x values, and therefore the corresponding y values are going to be. Because they want the coordinates. The coordinates means xy pairs, doesn't it? So we need the y coordinates for each of those 3 x coordinates. So we'll need to plug in here. which we simplified to this. So taking them each in turn, if x is pi over 2,
Yeah.
y value would be, I mean,
Pi.
if x is pi over 2, half of that, which is what?
It would be pi, wouldn't it?
Sorry, say again?
Pi x. Oh wait, what am I
No,
talking about?
what's
Pi.
half of,
Pi. It's pi, wouldn't it?
what's a half of half pi?
Oh, a half of pi over 2. A quarter pi.
Quarter pi, good. And then if we put pi over 2 in here, what's the sine of pi over 2? What time is pi over 2 on the clock?
90 degrees. So
Which has a sine value of what then?
over 0. No. Opposite 1. It's got y.
1. But what's the cos value of 90 degrees?
0.
So in fact, that's the end of story here, isn't it? That'll be 0 for pi over 2.
Yeah. Yeah.
And then what if our next x value was what? Pi. What time's that on the clock?
Pi is 9 o'clock.
Yes. So a half x is going to be what if x is pi?
Half x. Wait, say that again. If x
So
is
now we're
half.
plugging in pi into x here.
Okay, so half pi.
Half pi. And what about this term? What will that be at 9 o'clock?
Well,
What's cos of 9 o'clock first?
cos of 9 o'clock would be 1.
Don't forget, that's the
Sine
y-axis.
0.
This is the cos axis.
Wouldn't it just be 0 still?
Well, the term would be, because the sine is 0 here, yes.
Yeah,
Sine,
y would be. I mean, cos would be 1.
here's 1. Here's, because remember, this is a circle with x and y coordinates. Here's
Minus
an
1.
x coordinate of 1. Here's an x coordinate of
Minus 1.
-1. That's how you work out that cos of pi is -1.
Yeah.
Because you remember that cos, on the unit circle, the x coordinates are cos coordinates.
Right, okay.
But because sine is 0 at pi, you're right, that drops out again. So the next y value is half pi. And then the one you quite rightly pulled me up on, nearly forgetting, half of 3 pi was 3 halves pi. If we put that value of x in to here, what do we get?
What was it? 3 pi over 2.
Yes.
So you'd get 3 over 4 x pi. Sorry.
Yeah.
Um,
Now, where are we on the clock for 3 pi over 2?
we're at 10:30.
You're thinking of 3 pi over 4. Remember, the x value, 3 pi over 4 is from this part, but the x value was 3 pi over 2. What's the sine and cos of 3 pi over 2? Well, 3 pi over 2 is what time on the clock?
6 o'clock.
6 o'clock. So the
Yeah.
sine value there is what?
-1.
-1. But the cos value is
0.
0 because cos is x.
Yeah.
Okay. I hope you're beginning to you know, get on board with the unit circle.
Yeah, no,
A
definitely.
lot of people find it's you know, there's a lot to disrecommend it. You know, a lot of people just prefer not to. But I promise you, it's worth it. Right, okay, so here we've got the y values, quarter pi, half pi, 3/4 pi, for the x values of half pi, pi, and 3/2 pi. Weird, isn't it? So
Yeah.
the actual x, y coordinates are this then, I guess. Ooh. I mean, sorry.
Oh, you went for me.
And finally, it's a bit funny, isn't it? Still, that's, when I say it's funny, I don't. These are the y values. As long as we haven't made any errors, I don't see any reason to doubt that or think it too funny. Right. So those are going to be the coordinates of the points of inflection of whatever this curve looks like. I wonder what it looks like. Notice it's quite, you're adding a half x, you're adding that gentle slope, the y values on that, to sine x cos x, which we are guessing is going to probably be some kind of periodic waveform.
Yeah.
So it's all rather complicated. We're not going to graph it necessarily. We're just doing this with algebra. But we have found the points of inflection where the curvature changes from clockwise to anti-clockwise. Gosh. Right.
Okay.
So what happened there? A product rule necessary for differentiating, basically. Because what we're trying to do is get practice at differentiating. So you can get the integrating. Right, number 3. Okay, part A. So sine x over x, how shall we pass that?
Probably sine x, just the blob.
Sine x is the blob?
Yeah.
What's the outer function then?
1 over x.
Right, but I would say 1 over x is a function of x.
Yeah, I agree.
So it's not clear, if we put sine x as the blob, it's not clear what the function is of sine x.
Could it be like sine to the inverse sine x?
No. If you mean either power -1 literally, or you don't, sorry, so you mean what we sometimes call the arc sine of x. No, I mean, basically, because it's not working, I mean, don't take my word for it. Keep trying to make it work with this version or that version. But we are kind of hitting, well, I'm sort of, I should let the brick wall become more apparent here, but it is a brick wall. instead of treating it as a composite, what's the other possibility?
X is the blob.
Oh, but if you say blob, you're saying composite, inner and outer, aren't you?
Oh yeah. Yeah.
Inner
Okay.
and outer, composite, chain rule, not really working. Perhaps it's
Product.
product rule. Yes. Can we pass this as a product?
Yeah. So it would be sine x and x to the minus 1.
Exactly. We know how to deal with that, don't we?
Yeah. Okay. And then you'd get cos x.
Yeah.
X to the minus 1 times x to the
Yeah.
minus 1. Plus minus 1 minus x to the minus 2.
Yeah. Right. Minus x to the minus 2. Yeah.
Sine x times sine x.
Ah, yeah. What I would prefer to do is keep these the same way round so I can see, because as I say, we are being careful about the strict logic here. So I'm going to put that version second. And you're right, it's minus 1 times x to the minus 2. Now x to the minus 2, what I'm saying is, no, I'm being in too much of a hurry. I'm gonna say what you said. And now let's simplify. Well, I have turned that into 1 over x. So I could even write cos x. How could I write this? This term here.
Cos x over x.
Yes. And then this term is negative, so I'll put a negative what?
Negative x to the minus 2 sine x.
Yeah. But if x to the minus 1 can be rewritten as 1 over x, x to the minus 2 can be rewritten as
minus, so you've got the minus there, x over 2 sine x.
X over 2.
Yeah. Or sine x squared over 2.
So minus x to the minus 2 is minus x squared over 2.
No, you could say sine x squared over 2. Minus sine x squared over 2.
I don't know why you're squaring sine. It's not like we've got sine times sine.
No, you're not squaring the sine. It's sine x squared over 2.
Sine of x squared?
Over 2. You could make that all sine x squared over 2.
Could you? Really?
Well, you've got x over 2 and sine x.
Let's go step by step here. You've got x to the minus 2 sine x. We definitely could write it like that. So let's not be in too much of a hurry. Let's show that step. My point is, what's a nice way of rewriting x to the minus 2?
X over 2.
X over 2?
Yeah.
You're sure that x to the minus 2 just means a half x?
I meant 2 over x even. 2 over x.
Ah.
Yeah.
Well, I'm still not clear about that. For example, what's 10 to the minus 2?
Root x.
No. What's 10 to the minus 2?
10 to the minus 2 is it's not the same. Is it the same as minus root 10?
No, it's not, is it? What does the minus in a power mean? So if we work our way down from 10 to the power of 3, 10 to the power of 2, 10 to the power of 1, 10 to the power of 0, 10 to the power of minus 1.
Yeah, it makes it a fraction.
Yes.
So like 10 to the 1 would be a tenth. 10 to the minus 2 would be 100th.
Yes. 10 to the minus 3 would be 1 over
1 over.
cubed.
Yeah, so it'd be 1 over x squared.
Yes, it would. Yes. In other words, we've got sine x
over x squared.
Now what?
What we could do is say what we could do is cos squared x minus sine x.
No. Why cos squared x?
Because I made the denominators the same.
But then you want to multiply the numerator by what then?
Well, I've squared the top and bottom.
Ah, no, so that's an understandable error there. Just squaring top and bottom of a fraction does not keep the fraction equal and unchanged in value. Squaring the top and bottom of a fraction is like squaring the value of the whole fraction.
Okay.
So yes, you want to have x squared on the denominator, but you want to think, what have I done to the denominator? Not squared it. How else have you arrived at x squared on the denominator, apart from squaring x?
Timesing by x.
Timesing by x is how you want to think of it, yeah.
So cos x squared.
Oh. Now I am confused. What have you done to the numerator?
Times by x.
And what's cos x times x? It does sound a bit like I might have said cos of x times x. It sounds a lot like that. So I shouldn't have said it like that. But if you multiply cos x by x, you are not, if x is what you're multiplying cos x by, you're not looking inside the cos and multiplying the x by x. You're multiplying the whole of it by x.
Right, okay.
So what's the result of multiplying cos x by x?
X cos x.
X cos x, which is different, isn't it?
Yeah. Minus.
Oh, okay. So in the end, we've got what?
X cos x minus sine x.
We done?
I've forgotten where we started, maybe. Forgotten what we were trying to get to.
Well, let's not look back far. Let's just look back to here. Is this equal sign okay?
Yeah.
Really? So
No.
you're saying,
no.
23 over 7 minus 5 over 7 would be 18?
No.
No. What would it be?
It would be 18 over 7.
Ah, yes, quite.
So that's all over x squared.
Oh, yes, got to be, hasn't it?
Yeah.
But now we are done. We were just differentiating that. That's where we started, differentiating sine x over x.
Mhm.
Now, why was I so tempted to rewrite that like that? Because I knew there was a common denominator issue coming. And when you're differentiating a fraction, yes, write it as a product if you can, although we're learning something called the quotient rule. Do you know what a quotient is?
A quotient. Yeah, I have heard of quotients before, definitely.
And it's just a fraction, isn't it?
Yeah.
So the
Yeah.
quotient rule is the fraction rule. So the so-called fraction rule or quotient rule for differentiating really is just this, but it's written a bit differently. But it's the product rule really. And what it does is supplies a common denominator. It looks ahead here and supplies a common denominator like that. So if we turn 1 over x into x over x squared, we've already got that common denominator because we know where we're going to that stage there. So that will be something called the quotient rule. Good. Oh, next.